Hello, this is Mr. Waters again coming to you from Waters Studios, and this is another optimization problem for us to work on. Let me make sure that that's focused there. There we go. It's about as good as it's going to get. Okay, this one's got a little more going on, although not much more. And what I want to get at this is the reason why we're doing a further problem here is I want us to get used to the idea of using the steps to solve a problem and not necessarily just sort of memorizing how to do a certain kind of problem. Okay? So if you recall, I gave out a sheet, two-sided sheet that had the steps for solving solving an optimization problem, and there were 6 of them. Okay, one of the steps where you actually graph the thing, graph the optimization function isn't really necessary, so we're going to skip that in this problem here. Okay, so so let's read this problem here. Okay, which point on the graph of y equals rad x is closest to the point 1, 0? So let's read that again carefully. Okay, which point on the graph of y equals rad x, and as you can see, we've got a graph of y equals rad x, and then down here I'm going to make it in red so we can see it. That's where 1, 0 is. Okay, so the first step is to make sure we understand what we're solving for. We want to minimize the distance between some point xy on this curve and 1, 0. So I'm going to go ahead and put a point up here. So that's x, y. And what we're trying to minimize is that distance there. Let's call it d. So we want to find the point somewhere along here where this distance from that point to 1, 0 is the shortest. Now you can see that it's probably not going to be over here because that's longer than the one we pictured there, and then it's maybe going to be one over here. Maybe that's shorter, but you can see is I'm not trying to actually locate the point. I'm just trying to kind of visualize, what where that minimum distance would be on the graph. So keep in mind, it's this d that we want to minimize, and the quantities that we're optimizing are x, y, right? So now that brings us to step 2. And in step 2, what we're trying to do is we're going to try to write down, we drew the picture and labeled it, so that's what we just did as part of step 2. But then we're also going to write variables and expressions to represent the quantities that we're working with, and we're also going to bring in any formulas that relate the quantities that we're trying to work with here. In this case, the quantities that we're trying to relate, that we're working with, are x and y, the coordinates, and then the distance, right? So I'm going to say that x is equal to, the x coordinate of the point that we're interested in, and then y is equal to its y coordinate, right? Coordinate, right? Right there. Okay, and then, so now we need some more formulas that relate these quantities and which relate them to the distance which we're trying to get at, that we're trying to minimize. Now remember, in some of our earlier problems, we had area formulas, we had perimeter formulas, and we'll go back to those in a minute. But we want to think here, well, what's a formula that relates x and y? Well, that one, right? Y is equal to the square root of x, right? And then we also think, well, okay, so the distance, we want to minimize the distance. So what's a formula, like a stock template formula that relates the distance to these coordinates here? Well, that's the ye old distance formula. x1 minus x2, quantity squared, y1 minus y2, quantity squared. So this is an important part of the process here, where we specified what it is what we're trying to optimize and what we're trying to minimize in this case. And then we wrote down variables for the two quantities that we're trying to optimize. And then here are the formulas that we're going to work with, that we're actually going to use to write the formula, that we're going to use to find this minimum distance. Now, we did this in our earlier problems. Let me bring just sort of an image of our earlier problems back. Here is one of our farm pig pen problems, where we were trying to maximize the area, but we were given some amount of fence, which turned out to be the perimeter of this rectangle here. And this gave us another formula, 2x plus 2y equals 300, or actually in the case of our problems here, let me make that better, it was probably 1x plus y, right, because the wall there wasn't going to get any fencing. And then we used this formula here. Now we wanted to maximize this formula. So then what we did was we solved this equation for y, let's say, and that gave us a formula in terms of, and that would give us one equation in terms, and then substituted, and that gave us one equation in terms of x. And what I did here was, since it's not 2, that's going to be 1x, right? So we subtracted x from both sides, divide both sides by 2, and remember what we did then was we took this formula and we substituted into there to give us this, to give us that a of x, which was our basic formula that we were going to maximize. Or in our revenue problems, we had that the revenue was equal to the price that we paid for an item times the number of items that we made, right? But then we also had this demand formula, which gave us the price of the item in terms of how many we made. And then we took this formula and again substituted it back so that we only had one formula here in terms of x, right? And down here we even did the same thing with our box formulas. Here we wanted to minimize the volume of this box, right? Or actually, sorry, maximize the volume of the box. We said the volume was the length times the width times the height, and based on the conditions of the problem, we were cutting out these squares, and x was equal to the height. And then if we said that the piece of cardboard that we had was 20 by 14, it gave us a little formula for the length in terms of x, the dimension of the cutoff, and then a little formula for w in terms of x, the dimension of the cutoff. And then we substituted again both of these into there, and that gave us this complicated looking formula here, which we minimized. I'm sorry, which we maximized, right? Anyway, so so notice here it's kind of like there's a pattern. There's one formula, that one, and that one, that we want to either maximize or minimize, but then there was another formula or formulas that we would substitute in so that we would, for other unknown quantities, so that we'd only end up with one single quantity x, okay, which we would then find the derivative of and set equal to 0 so that we get the critical points, right? Okay, so back to here. It's the same situation, right? So here's the formula that we want to, in this case, we want to minimize. And then here is the other formula here that's equivalent to the perimeter or the price or the length and width formulas that give us y, that will give us x, well, actually give us y in terms of x, so we can substitute, all right? But first, we're going to go ahead, we want to minimize this distance. So now we can put all this together, actually, to write the formula, which is step 3. So the distance is equal to the square root of, and this is going to be since we want the distance from here to here, which is 1 comma 0, you understand, 1 comma 0, sorry, 1, sorry, I'm going to white out here. It's not at all what we wanted. We want x minus 1 quantity squared, because that's x1 minus x2, and then y1 minus y2 is going to be y minus 0 quantity squared, right? Well, this y is the same thing as that y, you understand. So we're going to simplify this a little bit. X minus 1 quantity squared minus y squared, right? This is x squared minus 2x plus 1 minus y squared, right? So far so good? Alrighty. Now, up here, since y is equal to the square root of x, y squared is equal to x if we square both sides. So now, this x goes over here where the y squared is, and again, same things we did on the other situations. We do a substitution so that we only end up with one variable. In this case, it's going to be x. So d of x is going to be equal to the square root of x squared minus 2x. Oopsie, and that's, of course, that's supposed to be a plus there, sorry. Hopefully this is not confusing you. That's all along, this is supposed to be a plus because it's plus in the distance formula. So that's a plus. So that allows this to simplify the way it's supposed to. X squared minus x plus 1. So the plus 1, the plus 1, the plus x, which went in for y squared, right? I FOILed this out and got that. This should be plus x here. We combine and we get this right here. And this is equal to d of x, right? Or, written in a form so that we can do the derivative easily, x squared minus x plus 1 to the 1/2. Now, so that's the end of step 3. And again, we've ended up with a formula that we're going to use to find this minimum distance. But instead of like before where we used, say an area formula and a perimeter formula, we're using the distance formula and the equation of the graph that this point x comma y is supposed to be on. Either way, the procedure, the concept is the same. So now I'm going to take this away, and we're going to put another page up here. Now, by the way, you should know that I'm going to be posting these these notes on paper so that you can look at them in detail. Okay. Plus, of course, you'll be able to rewind the video here. Let me get my hand and the pen in view. So this is going to be, here again, d of x is equal to x squared minus x plus 1 to the 1/2. Now this is step 4. Okay, we're skipping the graphing of the function part here, and we're just going to go straight to taking the derivative and setting it equal to 0 to find the critical point, right? So that's going to look like, if you want to, you can go ahead and graph this on your calculator to get a look at what it looks like. That would actually be, as always, a good idea. So d prime of x is equal to 1/2 x squared minus x plus 1 to the negative 1/2 times 2x minus 1. Chain rule, the derivative of the outside times the derivative of the inside, which is right here. And then, of course, to find the critical points, we set this equal to 0. Now, we've got to simplify this a little bit. That negative 1/2 means that this part, along with the 2, is going to be on the bottom of a fraction, and 2x minus 1 is going to be on the top. So we end up with this. And then it's 2 times x squared minus x plus 1 to the 1/2 equals to 0. Now we could write this part with a radical, but here's where it gets easy, because we're solving for x, right? Well, we just multiply both sides of the equal sign by x squared, by this entire denominator, right? And that cancels out. And when we multiply this part over here, of course, it zeroes out, and we end up with 2x minus 1 is equal to 0, or x equals to 1/2. Okay? So in other words, going back to, just for a minute, going back to this graph right here, the optimum point was x equal to 1/2, which is, oh, what a bizarre coincidence. It's about where I wrote it. Okay, does that make sense? Okay, good. Okay, so now we want to know what the distance is. At this point, we can go ahead and put 1/2 back into the distance formula. Okay, so here's number 4. We just found the critical point, which is at x equals 1/2. That'll give us the minimum distance, right? So now, step 5, we're going to find out what that minimum distance is by putting 1/2 back into the original distance formula here. D of 1/2 is equal to 1/2 squared minus 1/2 plus 1 square root of that. Okay? Let's hope that isn't going to be too much of a pain to evaluate. So that's 1/4 minus 1/2 plus 1. And I'm pretty sure that that works out to be the square root of 3/4. Which we're going to write as rad 3 over 2. And there it is. So that is the minimum distance to find the y coordinate, to find the coordinates. So this is the minimum distance, rad 3 over 2, right? And then to find the coordinates, we know that x is 1/2. Well, the y is equal to the square root of 1/2, because remember, y is equal to rad x, right? Which is equal to, after we simplify it, rad 2 over 2. After we square root the top and the bottom and then rationalize the bottom. So here's the answer. Our coordinates are going to be 1/2 rad 2 over 2. And then the minimum distance involved is rad 3 over 2. Okay, so that's how that goes. So now there's going to be another one on the upload that you should try out. There's a classwork where this one's presented, right, and a blank form, a blank version of the problem we just went through is going to be presented, so you can work through it on your own. Okay, then there's going to be a second one after that, right, which you can try out. Okay, it uses a different formula. It uses a parabola formula instead of a square root formula, but the concept should be the same. Okay, then once you've had a chance to try out that, I'm going to have a homework uploaded, which is actually what you've got to turn in. Okay, the homework will be a couple of these, one or two of these problems to try out, these distance formula problems to try out, maybe probably a repeat of one of our earlier optimization problems for us to practice with, and then some review problems involving the first derivative test and the second derivative test and the concavity test. Alrighty, well, very good. Thank you, and see you later. Bye.